Hello and welcome to another LeetCode problem. Today we're going to be doing problem number 1318, minimum flips to make A or B equal to C. And it's a problem of the day for June 6th or June 7th. And so this problem does use bit manipulation, but it's actually pretty straightforward bit manipulation. So as long as you know like logical OR, that's pretty much all you need to know, then you're going to be fine. And I will explain it real quick. So for logical OR, the way it works is when you OR two numbers, it means if one or the other number is a 1, then your result is a 1. So like if you have like this, one of these has to be a 1 at least for the result to be a 1. So for this, the result would be 0. And then for this, the result would be 1 because one of them at least is a 1. And then this would be 1, and this would be 1. So hopefully that makes sense. That's all logical OR is. This problem would be significantly harder if you're saying like swap the digits to and then add them and get C, but all you're doing is a logical OR. Okay, and so let's actually go through this first example. So, and I'll show you why it's not super difficult. So we have number A, number B. And so it's saying, what's the minimum number of swaps you can make in these two numbers, like overall, to make when you OR each one of these digits, the result is this down here. So let's figure that out. So for this case, the OR needs to be a 1. And so when you have a 0 and a 0, the minimum swaps you're going to need is you're going to need to change one of these numbers to a 1. Doesn't matter which one. So let's say we change this to a 1. Now let's just call it our result equals 1. So yeah, so when we're trying to get a 1, if we have two zeros, then we need to change, and let's write these down by the way. So trying to get 1, if we have 0 0, so yeah, then our result is 1. Okay, and let's keep going. So here we're trying to get 0 and we have two 1s. So when we're trying to get 0, both of these numbers have to be a 0 because in order to get a 0 you have to have two zeros. Okay, and so when we're trying to get a 0, if we have two 1s, that means we have to do two swaps. But if we're trying to get a 0 and we have 0 1 or 1 0, I'm just going to write 0 1 here, then we only need one swap. Okay, so hopefully that makes sense. So here we're actually going to need to do two swaps. And then this will add a 2. And then for this, so we're trying to get a 1. One of these needs to be a 1. It already is. And we're trying to get a 0. And so both of these have to be a 0. So those are the main things that we have to worry about is we're asking ourselves, okay, if we want a 1, then what are the cases we have? And we can just break this down into like a tree, right? So for 1, if we have 1 0, that's 0 swaps. So I'll just say that's r equals 0 here. Okay, if we have 0 1, then we're good as well. So r equals 0. If we have 1 1, r equals 0. And then, so the only case we care about is if it's 0 0, then we need to flip one of these to be a 1. Because, like I showed in the OR, in order for the OR of two numbers to be a 1, at least one of them has to be a 1. So then our result is 1 here. Okay, so those are our cases for a 1. Now let's look at our cases for a 0. So if we have a 1 1, so for a 0, we need both of our numbers to be a 0. So then we simply just count up how many 1s we have. So that's going to be 2. If we have 0 1, that's going to be 1. And if we have 1 0, that's going to be 1. Okay, so now we know how many flips we need to make, right? Like we can figure out, okay, what do we need and what do we have, and we can just figure out it's going to be one of these cases every time. But how do we actually go through our number and do this, right? So that's going to be the next step. So let's say we have numbers like, what are they in this example? So 2, 6, and 5, right? So we have A equals 2, B equals 6, C equals 5. So first of all, we're going to need to figure out how do we actually get the last digit, right? Like in this picture, we have to keep getting the last digit and compare. And so for 2, and I'm just going to draw this out. So 2 is going to look like this, and then I'll have some leading zeros just to make them all the same. And then B, 6 is going to look like this. And you don't need to know actually how they're presented. You just need to know how to get the last digit. And C is going to be like this. Okay. And so what you actually need to do to get the very last digit is it's pretty simple. You just take whatever number you have, like A, and you just do an AND. You just do a bitwise AND with 1. And so what that does is, like, let's say you have something like this, you AND it with 1. Now, what that does is it takes the last digit of your of whatever number you have, it ANDs it with a 1. And so if the last digit was a 1, 1 with a 1 would be a 1. If the last digit was a 0, then 0 with a 1 would be a 0. That's basically, that gives you the last digit of whatever you have. And so that's how you would get the last digit. So you get the last digit here, you store it. You get the last digit here, you store it. You get the last digit here, you store it. And then we do that comparison that I showed earlier, where we see what we're trying to get and what we have, and that's how many flips we need. So let's say we do get this last digit. Well, how do we get the next digit? So that's also pretty straightforward. So all you have to do is you do a bit shift. And a bit shift means, like, if you have something like this, you just say shift it to the right 1 bit. And what that does is, like, every bit goes to the right 1 bit. And then the rightmost bit gets deleted. So now that's going to turn to this. So we can simply get the last bit, then we can just shift everything to the right. Now this is the last bit. Then we shift everything to the right. Now this is the last bit, and so on. And then how do we have a stop condition, right? So our stop condition is going to be while C is greater than 0. That's going to be one stop condition, because, like, let's say we have a case where we have some A's and we have some B's. I'm just going to make it like this. And then we have some stuff for C, right? So we want to keep going for C, because even if B and A end, like, let's say this is this case, right? Even if B and A end, we still have to check all these bits to make sure we have to flip them, right? For the C case. So if C didn't end, but the other ones did end, then we still have to, like, see how many bits we have left and how many bits we have to flip. Now the other case is, what if C ends early and we still have bits for the other stuff? So it would be like this, right? So just say you have something like this, but then C is only like this or something, right? And so you would go through this chunk, and now remember, you'd keep shifting. So now your digit is here, but now your C is 0. And so you have to do the same thing. While you have an A and a B, you have to see, okay, let's keep going until I run out of numbers and see what I have to flip to make, because now you have to flip this to make all these ORs equal to 0, right? So if you run out of the numbers first, you have to make your stuff equal to 1. And if you run out of C first, then you have to make your stuff equal to 0. And so those are going to be our end cases. We're going to have a loop until C is 0. And then we also have to make sure that, we're also going to have to make sure that if A and B were longer than C, we're going to have to handle this case. And so those are our 2 stop conditions. So let's start coding it up, and I'll go over it as we code it up. And like I said, it's actually pretty straightforward once you figure out what you're doing. You literally just compare digit by digit, and you figure out what you need to flip. Okay. So we're going to have a result here, and then we're going to say while C is greater than 0. So that's going to be our first end condition. We're just going to go through the numbers until we don't have a C anymore. And so we're going to take the bits. So we're going to say, like, A bit, B bit, C bit equals, and this is, so you do this, A and 1, B and 1. So this will give you the last bit of whatever number you have, C and 1. Okay, so now remember, what are our cases? So we have a couple cases. One is if C is 0, right? So if the last bit is 0, or let's handle the one case. So we'll just say if C bit, meaning if the C bit is 1. So I'll just write it just to make it easier as well. So if C bit is 1, then what do we need to do? Well, there's a couple cases, right? So if C bit is 1, remember, if A and B are both 0, so let's do that first maybe. So if A bit equals 0 and B bit equals 0, now remember, we have to flip just one of them to be a 1. And so we don't actually have to do the flips, we just have to calculate how many flips we do, right? So we just add to the result, and then we can shift. We don't actually have to do the flips. Okay, so we're going to add 1 to the result here. And then what are other cases? So remember, if any other case, but I just tab this a little. Okay, so for this A bit equals 0 and B bit equals 0 thing, if there's any other case, right? If we have 0, 1 or 1, 1, or, right? So, like, in order for this to be a 1, if we have 0, 1, or if we have 1, 1, or if we have 1, 0, we don't actually have to flip anything. So this is the only case we need to care about. If C is 1, then if they're both 0, we need to flip 1, and that's it. Okay, now we have our else case, and let's figure out what we need to do with that. So the else is when C is 0. So if C is 0, we need the A and the B bit to both be 0. So let's say they're both 1 to start. So if A bit equals 1 and B bit equals 1. What do we have to do to make it 0? Well, they both have to be 0, so we're going to have to flip them both. Now, what is another case? So the other case is we either have 1, 0 or 0, 1. Either one of these, we'd have to flip 1 bit, and it doesn't, and they both be 1 bit, right? So we can just say, now that we have the and, we can have, so this would be an else if actually, a bit equals 1 or b bit equals 1. And so if they're both true, then it'll go here, and then this is the case if it's 1, 0 or 0, 1. Now we do res plus equals 1. Okay, so remember, this handles everything. This is if the C bit is 1, this handles the logic for if the C bit is 0. Hope I did that right. It is easy to screw up. And now at the very end of here, we need to go to the next bit, right? And so how do we do that? Well, like I said, we just shift it to the right. So C equals C shifted 1, B equals B shifted 1, A equals A shifted 1. Okay, and so this loop will happen while C is 0, but remember, or until C is 0, but remember, when we run out of C, like what if our A is like 1,000 or B is 1,000 or whatever, and then our C is like 5? We're going to run out of C way before we run out of the other ones. So now we need to also go through the rest of it. And so that's pretty straightforward. So we can just say while A or B, right, as long as one of these, so say A is greater than 0 or B is greater than 0. Okay, now let's get the A bit and the B bit again. So A bit. And the thing is, the nice thing about this is, like, let's say our A is still a number, right? Let's say our A is still this, and our B, if your number is 0, it's just gonna stay 0, right? Like 0 shifted to the right one is still 0. So we're just always gonna get a 0 for whatever one is 0. So that's totally fine. Okay, so A bit, B bit equals, remember we want to get the last bit here, B. Okay. And so now what do we do? Well, the only case we have, the C bit is 0, right? So if the C bit is 0, we want, what cases can we have? Well, we can have the case where they're both 1. So it would pretty much be this. Also, let me copy some of this and then change it around maybe. So if A bit is 1 and B bit is 1, right? And we want them both to be 0, then we have res plus equals 2. Otherwise, if one of them is 1, then it's res plus equals 1. Because we're trying to get 0, and the only cases we care about swapping is these two, this case where we need to add 2, or one of these, where it would be 1. And so this handles where they're both 1, and this handles if it's one of them. Okay, and then we have to do the same thing, right? So we have to do these shifts. And so this will guarantee now that we go through every single number. Then we simply return res here, and hopefully I did it right. Okay, hopefully. Nice. Okay, so let's go over the time and space complexity here. Yeah, and so hopefully that makes sense to you. It's a pretty straightforward algorithm once you realize you're not trying to add here or something. I did think of that before, where like they put these numbers as if like you're trying to add. If you're trying to add, it would get tricky because you'd have like carry and stuff. But because you're trying to OR, you can simply compare digit by digit, and then you only have a few cases to check. You know, there's only 4 possibilities or 3 possibilities you care about total. Okay, so time. So we are going through every single number, right? And we're going through one digit at a time. And so what that would actually look like for time complexity is, well, let's say you have a number like 8, right? So let's say you have a number like 16 maybe. So 16 is like this, I think. And so if you're going one shift is the same thing as dividing by 2, right? So for example, this is 16. If you shift this over here, now it's actually this, right? Because this goes away. So this is 8, right? So 2, yeah, this is 8, this is 4. So one shift is the same as divided by 2. So technically what you could do if you wanted to was you can literally just, instead of these shifts, you can just say divide by 2. And that would be a valid, that would be the same thing. But the thing is, so we're going to go through these, and the complexity is going to depend on the biggest number we have, right? Because we're going through while C is greater than 0 or while A or B is greater than 0. And so the biggest number that we have is gonna like set our complexity. So our time complexity is actually gonna be like the max of A, B, C. And it's gonna be the log of that, right? Because this bit shifting, we're always dividing by 2. So it's like if 2 if 2 to the n equals our biggest number, whatever the ABC is, then, like let's just say A, then our complexity to go through this operation is n times, and it would be log of the biggest number you have. So it would be like n equals log base 2 of A, like that. And so this is actually a logarithmic logarithm, and you can kind of see that too, right? Like 4 bits would be 8, but we only have 4 operations and so on. So once these numbers get really big, like you're still only comparing 1 bit, right? So let's say you have like this is 8, this is like 16, this is 32, 64, but you're only adding 1 bit, but you really keep doubling your number. So, but the work is like a lot less. You're like, we're not going through every single, if we have a number like 64, we're not checking 64 bits, we're only checking, 8 bits. So that's why it's a logarithmic function. Okay, and space is, oh, so we're not really making any data structures, right? We just have a result, so space is of 1. Okay. And yeah, so I guess technically if this is 10 to the 9th, this would be like log 10 to the 9th would be our like worst case scenario. But yeah, it's definitely going to be the biggest number, because you're going to, if A and B are bigger than C, then this loop will end first, and then you'll have to go through this. If C is bigger, then you're going to go through this, and then you won't even get into these because you'd have already gone through the numbers. So hopefully that makes sense. It's definitely not a super hard bit manipulation problem, as long as you know basic bit manipulation, just like how to manipulate 1 bit. There's definitely tons of harder problems, but definitely does look intimidating when you first look at it, but once you get into it, it's not so bad. So hopefully you like this problem, and if you did, please like and subscribe to the video, and I'll see you in the next one. Thanks for watching.